is a video for lecture 3. The topics include electron configuration and periodic trends. So for electron configuration, what that means is talking about an atom of an element and thinking about where the electrons are located. So if we think of hydrogen, which is atomic number 1, which means it has 1 proton and 1 electron. That 1 electron is outside of the nucleus, and we think of it kind of like on a shell or orbit, and it moves around the nucleus. And then as we add more electrons for different elements, we need more space for the electrons. So helium is the next element, and helium has 2 protons and 2 electrons. And you can have up to 2 electrons on the first shell. As you move further from the nucleus, there's room for more electrons, and we're going to have like compartments of where the electrons are located. So if you studied chemistry before, you might have studied the electrons being on like rings, but it's a bit more complicated than that. We want to think of the rings as being more three-dimensional and the electrons being in spaces. So this would be similar to like a person being in a room. And so a good analogy of this model that we're going to use is a hotel or a apartment building. So if we think about the apartment building as having floors, so there's floor 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is the ground. So if you live on the first floor, you live, close to the ground, but as you move further away from the ground, you might take an elevator and go up to a higher floor, and there's room for more people. The floor would be similar to the energy level. And so we use numbers for the energy level. So we might say energy level 1, 2, 3, or 4, just like we would say floors in an apartment building. And another word we could use for energy level is called a shell. So it's kind of like a three-dimensional ring. And then if you live on the second floor, there's multiple apartments. So maybe you live in 2A. So 2A would be one of the apartments on the second floor. So the floors are broken down into smaller compartments called apartments, and with the atom, they're called subshells. And just like you can have different size apartments, you can have different size subshells. And then within the apartment, you have rooms. So maybe you live in a one-room, studio apartment, or maybe you live in an apartment that has 2 bedrooms and like a living room space, and so there's like 3 rooms. And the word that we use for chemistry for the atom where the electron is that's similar to the room is called an orbital. So in an apartment building, you might live on the 7th floor, you might be in a certain apartment like 7B, and then you might share that apartment with someone else, but you have one of those bedrooms. That would be like the orbital. So we're going to say where the electron is located by the energy level, the subshell, and then the orbital. So this is going to seem a bit confusing at first, but as we get into some examples and you see what you need to be able to do, you'll see that there's a pattern and it's really related to the periodic table, so it makes it pretty easy. So the type of subshell gives you the number of orbitals. So the S subshell has 1 orbital, the P subshell has 3 orbitals, the D subshell has 5 orbitals, and the F subshell has 7 orbitals. This would be like similar to the size of the apartment. So if it had a 1-room apartment or a 3-room apartment. Right, so an orbital is a space where you can have up to 2 electrons, and in a bit we're going to look at a diagram that shows arrows that represent the electrons. And so we'll have a box, which will be the orbital, and to represent the electron, we'll actually use an arrow, and we'll do an up arrow and a down arrow. And what that represents is you can have two electrons in an orbital. Similarly to like maybe you could have 2 people per bedroom. So if an s subshell has one orbital, you can have 2 electrons. If a p subshell has 3 orbitals, that's like 3 rooms. That has 6 electrons. If something has 5 orbitals, you can have up to 10 electrons. And then 7 orbitals can have 14 electrons. The shape is not too important for us. It's just the idea that it's a 3-dimensional kind of space of the atom. An S subshell looks like a sphere. A P subshell looks like kind of like a bow tie. A D subshell looks kind of like butterfly wings, like if the bow tie was doubled. And then the F would be kind of like that with a multiple piece. So something like that. And then we're going to go over the different subshells that exist for each energy level. So the energy level closest to the nucleus, that's called the ground state, you only have room for 2 electrons. And then as you move further from the nucleus, there's room for more electrons, so there's more like orbitals or spaces. So in the first energy level, you can have an S, and so you can have up to 2 electrons in that S subshell. On the second energy level, there's an S, but there's also a P. So now you have room for more electrons. You can have 2 in the S and 6 in the P. So that adds up to 8. On the third energy level, there's an S, a P, and a D subshell. And so the S can have 2, the P can have 6, and the D can have 10 electrons. So that adds up to 18. And then as you go to the fourth energy level, you can kind of see a pattern here. We're going to start to see an F subshell. So there's an S, P, D, and F. So even though this is, sort of confusing, there is patterns to this. So the S can have 2, the P can have 6, the D can have 10, and the F can have 14. Okay, so there's 2 types of ways we're going to express the electrons and where they're located. One is orbital notation, and the other one is electron configuration or notation. So if we were looking at neon, and when we go to do these problems, you want to have a periodic table available. So if I look at neon on the periodic table, something we learned last week is a neon atom, because it's atomic number 10, would have 10 protons. And for our purposes, a neon atom that's neutral will also have 10 electrons. So we want to have some way to denote where those 10 electrons are located. And so the rule is the electrons are always going to fill the spaces close to the nucleus and move further out. So we're going to use arrows to represent the electrons for the orbital notation. So what we're going to do is we're going to do an arrow up and an arrow down in the 1s box. And then moving up represents occupying the electrons with slightly higher energy levels. And so the second energy level has an S and a P, but you can see the S is slightly lower than the P, and that's the pattern that's going to follow. The electrons will always fill the S before they go to the P. Now you can have 2 electrons in each orbital. For the 1s, it's just 2 electrons in each s orbital. There's only 1. When we get to the 2p orbital, there are 3, or 2p subshell, there are 3 orbitals. This would be like if you got on the bus and there was someone sitting in a seat, but next to them there was no one there. You would more likely probably just sit in a seat by yourself rather than pair up with someone. And that's what happens here, where the electrons will fill this space by being in separate boxes first. So if I had 2 electrons in the 2p, it would look like this. If I had 3, they would be in separate boxes. Then if I have more electrons, then they'll start to fill up or double up, and we just go from left to right. So if you count the arrows, that's 10 arrows, which represents 10 electrons. So this would be a notation of showing where the electrons are in the neon atom. We also write it a different way, where we don't show arrows and we write what's called the electron configuration. And so if we think about this right here, this is 1s and there's 2 electrons. So what we write is 1s2 instead of drawing the arrows. And then when we go to 2s, it's the same thing. There's 2 electrons there. So we write 2s2 to represent 2 electrons in the s subshell on that second energy level. And then for the 2p, there's 6 electrons, and so we write 2p6. So these are showing the same thing or same idea for neon with 10 electrons. And when you look at the superscript, that number there, that tells you how many electrons are in that space. So S can have up to 2, P can have up to 6, D can have up to 10, and F can have up to 14. But if it's not filled, it's possible to have less. So again, this just shows kind of the orbital notation and how the electrons occupy. So orbital notation is used as a way to represent the location of electrons in the atom. You use a box to represent the orbitals, and you add arrows, one up and one down, to represent up to 2 electrons in an orbital. And electrons will occupy separate orbitals within the same subshell before they pair up. So this is kind of like an idea of what the atom would look like with a lot of electrons. So this is showing like a zoomed in part of this here. So this would be the nucleus where the protons are. And then there's like these shells. So this is the first shell, which is the first energy level. And then this is the second shell where you can have an S and a P. So, you know, for that notation, we write 1s2 for that. And then for this one, we write 2s2, 2p6. And then you can see as you move further out, there are more subshells. So on the third shell or energy level, there's 3 subshells. There's the 3s, the 3p, and the 3d. And then on the fourth energy level, there's the s, p, and d, and f for that those subshells. All right, and then if we kind of move on here, let's look at these examples specifically. So the first thing you want to do is find the element on the periodic table. So lithium is high up on the periodic table. It's atomic number 3. That means it only has 3 electrons total. And so this will be pretty easy. We're going to go up, down in the 1s, and then we'll just do an up arrow in the 2s. So the first arrow is always up, and then the second arrow that you pair up is down. All right, carbon has 6 electrons. So to show 6 electrons, you're going to go up, down in the 1s, up, down in the 2s, that's 4 electrons, and then we just need 2 more. So we're going to go up, up in the 2p. All right, neon we already did, that was 10 electrons. It was up, down in the 1s, it was up, down in the 2s, and then the 2p is complete, but I like to fill it in the way that it would. So I would do up, 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 so they're in separate boxes, and then do down, down, down until you get the 10 that you need. Okay, if we look at phosphorus on the periodic table, it's atomic number 15. So it's 15 electrons. And it's going to be like neon with more electrons. So let's start by doing up, down in the 1s, up, down in the 2s, up, up, up in the 2p, down, down, down in the 2p. Okay, that's just like neon, that's 10 electrons, but we need 5 more. So we always go to the S before the P, so we fill the 3s. And then that is 12 electrons, so we need 3 more. So we're going to go up, up, up in separate boxes in the 3p. Okay, those are pretty small atoms with a small number of electrons, but we're going to have to do them for like a little bit longer electrons or bigger atoms with more electrons. So I'm just going to show you the order. We're basically just going from the bottom to the top, and that's representing having the electrons occupy the lowest energy. So we do the 1s and then we do the 2s. So you might want to just draw connecting lines between them. And then after 2s, we go to 2p. Then we go to 3s and then 3p. Now, in the third energy level, there's a d subshell. But if you look at the order from going up, the 4s is a little lower than the 3d. And so there's this pattern where we're not going to go to the 3d, the d or the f before we fill the s and the p, or the s rather first. So we're just going to connect these. So after 3p, we're going to go 4s. and then from 4s we'll go to 3d, and then from 3d we'll go to 4p, to 5s, and then over here to 4d, and then 5p, and then 6s, and then we're going to go over here to 4f, and then 5d, and then 6p, and then 7s, and then over to 5f, and then over to 6d. And we probably won't have examples that need all of those spaces there, but again, that's the order that the electrons occupy. If we had to do problems like this on the test, there'll be some reference to help you with that order. Okay, so that was orbital notation. Now we're going to do electron configuration. And all of the elements start the same way. So again, you'll see a pattern form, and there's very much an order related to the periodic table that once you see that, it'll become very easy. So this is lithium. Lithium had 3 electrons. So we did the orbital notation earlier, so it's 1s2, 2s1. Carbon had 6 electrons, so it was longer. It was 1s2, 2s2, 2p2. Neon had 10 electrons, and phosphorus had 15 electrons. Okay, so we're going to do argon. So we go to the periodic table and we find argon on the periodic table, and it's number 18. So it's going to have 18 electrons. And you could use this here to help you as you're filling it. But they're all going to start the same way. So if you use phosphorus kind of as a guide for this one to start, all of them start with 1s2. So the electrons are going to be in the 1s to start. Right? From there we go to 2s. So in the second energy level there's an s and p subshell, but we fill the s and then the p. So it's 2p2, 2s2, and then 2p6. Okay, after the 2p we're going to go to 3s, so it's 3s2, and then 3p. And p can have up to 6. So what we want to do now is look at the superscripts and add them up. So we have 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 16 is 18. So that's what we needed. So this is the correct electron configuration. And you can notice that it ends with the P being filled, P6, which represents something about the argon being a noble gas and having complete electron configuration. Right, now we're going to go and do titanium. So if you look at titanium on the periodic table, it's number 22. So they all start the same way. So we're going to go 1s2, then we're going to go 2s2, and then 2p6. So that would be having the first energy level and the second energy level filled. Now we're going to go to the third energy level. We always do s before p, so it's 3s2, 3p6. All right, so there is a 3D, but if you remember from the ordering here, we do 1s, then 2s, then 2p, then 3s, then 3p, and the 3D is a little bit higher energy than 4s. So we're going to go to 4s first, and then 3D. So after 3p, we're going to go to 4s2. And if we add up the superscripts, that adds up to 20. But if you remember, titanium is 22, so we need 2 more electrons. So after the 4s, if you look at that order, we go to 3d. Now d can have up to 10, but we only need 2 more, so we're going to leave it as 3d2. And that would add up to 22 electrons for titanium. All right, europium is a lot bigger. Europium is way down here. It's number 63. So this is going to be quite long. But if we can do something that's long, then we can kind of see the order that they fill. So we always start the same way. So we're going to do 1s2, and then 2s2, 2p6, and then 3s2, 3p6. Okay, there is a 3D, but we're going to skip it right now and go to 4s first, so it's 4s2. And now we can go to 3D, and it's 3d10. And so we did the 4s already, we went back to the 3D. Now comes 4p, so it's 4p6. And if we look at the order after 4p, we're going to go to 5s. So it's 5s2. And then there's a 4d, so it's 4d10. And then we go back to 5p, so it's 5p6. All right, so let's start to add up the superscripts. We have 2, 4, 10, 12, 18, 20, 30, 36, 38, 48. This would be 54. So we need to get to 63, so we have a little bit more. After 5p here, we're going to go to 6s, and then after 6s, we're going to go to 4f. So we're going to do 6s2, and then we're going to be at 4f. Now f can have up to 14, but we might not need 14. So we had 54 before, now the 2 more would be 56, and we need to get to 63. So that's going to be 7 more, so it's going to be 4f7. Double check that. So 2, 4, 10, 12, 18, 20, 30, 36, 38, 48. This part here is 56, and we need to get to 63. So if we add 7 more would give us the 63 that we need. Okay, so that's a little bit challenging. We're going to see that there's a correlation to the periodic table that will be helpful for us. Another thing that we can do is we can shorthand the electron configuration, and the way we do that is we use what's called noble gas configuration. So this group here is on the periodic table. It's group 18 on the periodic table, and they're all noble gases. So the reason why we can use noble gases to shorten the electron configuration is because noble gases have full shells. And so what you're doing is you're just showing the outer valence shell by using a noble gas to shorten it. So we're going to be using the same examples that we did up here before, but we're going to shorten them. So if we look at carbon, carbon was atomic number 6. To shorten it, you have to use a noble gas that's just smaller than this. So we're going to use the helium, which is 2. So what we do is we put helium in brackets. And what that does is if we go back to the notation that we have for carbon, the helium is that first part, the 1s2. So the part that's after it, we have to still keep and add on to. So we're saying it's like helium, 2s2, 2p2. Now that doesn't really shorten that configuration too much, but it really shows or focuses the valence electrons, which are on the outside of the atom. All right, neon's actually a noble gas, but again, we want to show the valence shell or valence electrons. So to shorten neon, we're going to also use helium because we can't use neon to shorten neon. And then the stuff that was added after helium was 2s2, 2p6 for neon. Helium is atomic number 2, so if you add up 2 plus 2 plus 6, it gives you the 10 that you had for neon. Okay, phosphorus, if we go up to phosphorus example, it looked like this. So it had 15 electrons. So for phosphorus, we can use neon to shorten it. So we're going to put neon in brackets, and we're saying phosphorus is like neon's configuration. The first 10 electrons are like neon. And again, if we just keep going back to our example, the first 10 electrons would be 2, 4, 10, would be this part right here. So instead of writing this first part, we're putting any in brackets. And we're going to have to add this last part. So it becomes 3s2, 3p3. Okay, argon is also a noble gas. It has 18 electrons. So we're not going to use argon to shorten argon. We're going to go up and use neon. So we'll use neon again. Neon will be the first 10 electrons. And if you go back to that example before that we did for argon, The ending part was 3s2, 3p6. So again, we need to add up to 18. So we have 10 from the neon, and we have 8 that we've added after that. Okay, titanium was atomic number 22. So if we look at our choices for our noble gases, the noble gas that's just smaller than 22 is argon. So we're going to start by putting argon in brackets. And then we just have to show 4 more electrons to show the 22 minus 18. So if we go back to our example, the last 4 electrons would be these. And so those are the ones that we're going to put at the end. These beginning electrons, what we're doing is we're shortening and saying it's like argon. And so we're using argon in brackets in place of all that. So again, we're going to use 4s2, 3d2 here at the end. Okay, europium, that big long one that we did earlier, had 63 electrons. So we're going to use xenon to shorten it, and that should shorten it a lot. So the first 54 electrons would be because of xenon. And if we're trying to get to 63, then we need 9 more electrons. So if we go back to our example, the last 9 electrons, these ones here, have been added after the last noble gas. So we're shortening this quite a bit because we're taking that first string there and saying it's like xenon, and then we're using this last part at the end of our example. So 6s2, 4f7. Okay. So this is what I was talking about as far as like understanding that there's a trend in the periodic table to help make it easier to write the electron configuration. So if you start here at this element and you think about the order and you look at the structure here, we have 1s and s can have up to 2. Sometimes this box here will be over here for the purpose of this, but not usually. So this would be 1s1 and then 1s2. And then as you go across row 2, you can see you're going to fill 2s and then 2p. So this is the S block. This is where S gets occupied. So if you're in the first column, it's S1, and if you're in the second column, it's S2. And then this is the P block. And P can have up to 6. So P1, P2, P3, P4, P5, P6. There's 6 boxes to show that P getting up to 6 electrons. Remember, D can have up to 10 and F can have up to 14. But you really can see some order here, and it makes it a little bit easier to write the configuration. So let's try writing out some electron configurations, for example, just by where it is in the periodic table. So let's find this element here. So if we go to the main periodic table, the element that matches that is aluminum. This is aluminum right there. So if I wanted to write the electron for aluminum, and I just knew it was in this box here, I'm just going to go across and start to write the order. So as I go across row 1 and I'm past that, I'm going to write 1s2. And as I go across row 2, I'm going to start by filling the 2s, so I'm going to write 2s2. And then I'm past the 2p, so I'm going to write 2p6. So going across the first row on the periodic table, the first 2 rows represents going across 1s, and then 2s, 2p, and then we're trying to get to here, so we're going to start to go across row 3. So we'll see it's 3s2, 3p1, because it's just one in the first box. It's in the third row, and this is the P block. Okay, we're going to do a shorthand one, and you'll see how easy it is with this method. So let's find this element right here. So that element right there on the periodic table is radium. So let's say you wanted to do the shorthand configuration for radium. So this is group 18 here, and if you remember from the example, it was helium, neon, argon, krypton, xenon, and radon. So if you get an example and you can shorten it, we're going to start with that noble gas. So this here is the element we're trying to get to. So to shorten it, we're going to go up one row and all the way to the end. So the noble gas at the end of row 6 is radon. So if I'm doing any example in row 7, I can shorten it by a lot and say it's just like radon with a little more stuff. So after I write out radon, now I can go across my last row until I get to this box here. So I'm in the 7th row, and this S is the 7S. So we're going to write 7S2. And that's it. That would be the shorthand electron configuration for that example. Things get a little tricky with the F subshell, writing that out. We just need to remember that it fits into the periodic table like a puzzle piece. And so again, as you go across the rows, the S and the P are the same as the row. So you have 1S, 2S, 2P, 3S, 3P. And then if you notice, as you go across row 4, it's 4S and 4P, but the D is one less than the row number. So we want to learn that pattern. So 4S, 3D, 4P, 5S, 4D, 5P. And then if you were to go across row 6, you actually need to go 6S and then down to the 4F, fill that, and then you go back up to this row 5D and then 6P. I don't think we're going to see examples, maybe in the practice a little bit, but probably not on the test. It's just the main group elements with the S, D, and P. Okay, the last thing that we need to be able to do is just identify the elements as being metals, nonmetals, or metalloids. So what we're going to do first is we're going to draw a staircase to represent the separation. So if you could go to where the corner is here with boron, and we're going to go down and across and make like a staircase on the periodic table. And this is going to divide the periodic table for us into categories. And so the 3 categories are going to be metals, nonmetals, and metalloids. And so we'll do the metalloids first. So the metalloids, there's 6 metalloids and they border the staircase. And so boron, silicon, germanium, arsenic, antimony, and tellurium. Okay, these would be the 6 metalloids. And then we'll do the nonmetals next. The nonmetals, are to the right of the staircase. So carbon, nitrogen, phosphorus, oxygen, sulfur, selenium, fluorine, chlorine, bromine, iodine, acetine, and then all of the noble gases. Those are all considered nonmetals. So pretty soon we're going to talk about the elements and different characteristics they have, and we want to use the right terminology. So the nonmetals are on the right side of the periodic table, and then we're going to, oh wait, there's one more nonmetal. So hydrogen's on the left side of the periodic table, but it's classified as a nonmetal. And then the whole rest of the periodic table are metals. So these are very reactive metals in the first 2 groups. And then these metalloids in the middle, or metals in the middle, are a little less reactive and more common, like copper, gold, zinc, lead, platinum, tin, aluminum. And then again, these 2 rows fit into the periodic table like a puzzle piece, so they're still to the left of the staircase. So those are considered metals too. So that's the end of the first part of this video. Thank you.